Good day, ladies and gentlemen. So this is part 2 of chapter 11, and today we're going to mainly look at records and also start off a little bit with linked lists as well. In the previous lecture we talked about arrays, so as a data structure, and today we're continuing with records. So records are a collection of related elements, possibly of different types, having a single name. So very similar to the concept of an array. We will look at some specific differences in just a while. Each of these record elements is called a field. So basically it means that a record is made up from a number of fields. Now a field is the smallest element of named data or of this record that has some kind of meaning. Also, a field has a certain type, and it exists in memory just as records, although a little bit more technically different. We will look into that in just a while. So fields can be assigned values, which in turn can be accessed for reading or manipulating them. So a field differs from a variable primarily in that it is part of a record. So as a matter of fact, a field is actually just a variable, but it is a variable that very specifically is assigned to or belongs to a record. So we can say that the elements in a record can be of the same or different types, but all elements in the record must be related. What do we mean with that? Let's look at this example. So in this example, figure 11.7, it contains two example records. The first one here is called fraction. So fraction is the name of this record structure, and it has two fields. The two fields have names, and the name for the first field is called numerator, and the name for the second field denominator. So this is a way in which we kind of simulate how to store the value 13.17, literally, by splitting them up, and basically to have the numerator in a separate variable, which is then 13, and the denominator in a separate variable, which is 17, or 17 rather. And as I say, this would represent 13.17 as an example. Perhaps a bit more practical example is the student example. So this student record here basically have three fields, and now you can see the first field here is called ID, and this is typically, in this particular case, it is simply an integer field. So the type of this ID field is an integer. The next field is called name, and that's basically the name of the student. And take note that usually a name is stored in the form of text characters, and a number of them, as you can see here. George Bull is the name of this student, which basically is just a number of characters grouped together, and usually in the syntax indicating that this is a text string, we basically use these double quotes, the ending and starting of the double quotes. Everything between those double quotes simply mean that that represents a string. The last field in this record is called grade. So this typically is just an A, B, C, D, and so on, representing a letter grade, and the type here is character. So that means that this field can only store a single character, and usually in this scenario, or in this case where we use the character type, we basically use single quotes, just as a matter of syntax. So basically the name of this record is student, and this student record contains three fields: ID, which is of type integer, name, which is of type string or character of strings if you want to, and grade, which basically is a character type. So just so that you know, you could have used the string here as well. A string may also consist out of just one character, but there is a very specific type that we often use in computer science in this programming, in programming, which basically is character, which means it can only be one character. Right, so let's start looking a little bit closer at some of the differences between records and fields. So just as in arrays, we have two types of identifiers in a record: the name of the record, the name of the record itself, and the name of each individual field, as you saw in the previous examples. The name of the record is the name of the whole structure. So like student, in the previous example, the student record is the name, student is the name of that entire structure consisting out of the fields, and each field allows us to refer to that field alone. In other words, most programming languages uses a period or a dot to separate the name of the structure, which is basically the record name, from the name of a particular field. All right, and we'll look at some example just here below. So in this example, the student record that we just saw on the previous page, the name of the record is student. So that's referring to the entire structure. And the name of the fields. To access the ID field, we then usually use the name of the record structure, student, then followed by a dot, and then followed by the name of the field. So student.id means we only now referring to the ID field in the student record. Similar to student.name, that is used to access the name field, and student.grade is used to access the grade field. Okay, so this is the convention that we're going to use in this course as well. Other programming languages might have slightly different syntax, but most programming languages actually uses this kind of syntax when accessing records and specifically fields in those records. So here's an example. It shows the value of those fields. In other words, if we say student.id is assigned the value 2005, basically we can do that with programming syntax by saying student.id equals 2005 or 2005. Similar to the name, student.name equals g.bool, and again remember for the string type we have the double quotes, and student.grade is equals a, which will assign a to the student.grade field, and again remember that we assume this is a character type, so therefore we use single quotes. So further comparing records and arrays, we can conceptually compare an array with a record. So conceptually, both of them are structures and both of them store data. So this helps us to understand when we should use an array and when we should use a record. And later then we'll also see when to use, for example, a linked list. Anyway, an array defines a combination of elements of the same type. So this is very, very important. Always with arrays, always have the same type. All right, so be aware of that. You cannot have an array actually where some of the content of a particular array are strings and some of the contents are integers and so on. For arrays, you can only use one type. while a record defines a collection of fields, mostly with different field types. Some of the types might be the same, but mostly the types of the fields may differ. Like the student example we saw. The student ID was an integer, the student name was a string, and the student grade was a character type. So there you can see all three are different types. You may sometimes have certain fields with the same type. So say for example, the student ID field, which we know is an integer, and for example there could be another field called let's say a year. All right, so a year could be value 1, 2, or 3, indicating first year, second year, or whatever, and that could also be an integer. So it's not a problem to have several fields that also are of the same type, but obviously the difference is that their names must differ. You cannot have two fields meaning or supposedly different fields with the same name. They must all have unique names, field names. Again, for an example, an array can define the class marks of students. So there are 40 students, and then just the class mark for each student can be saved in that array. But nothing else is saved in that array. No, in other words, not even name, student number, or anything else. Then if it just has to save one type of data, then basically we use an array. But a record defines different attributes of a student, like as we saw, their ID, their name, their grade, etc. An array of records, we can certainly do that. We may have an array that consists out of records, so that is actually possible. And in this example that we see here, so we can have an array called students, and each array value hosts basically, so this entire array value here hosts a record structure. So technically speaking, it's a record type. All right, and for that reason, it means that array technically stores a record type. All right, but we know by now that a record now can be further subdivided into different fields like ID field, name field, grade field, and so on. And so this just gives you an indication, how the fields would differ for each record entry, basically. In this example, shows how we access the fields in each record in the students array to store values in them. So now things start to look a little bit more complex. Basically what this says here is that students1 dot ID is assigned the value 1001. In programming terms, how the syntax look like is usually like this: students1 dot ID equals 1001 semicolon, depending this usually for Java, C++, C, and so on. But the thing that you should note here is that let me just jump to the last point here. Look at the brackets around students1. And this is very important. Otherwise, if you forgot to put the brackets around, then you'll still learn about this in programming languages, but some of the operators, we very often talk about this dot as an operator, but we also get other kinds of operators which basically are brackets, round brackets, and square brackets. They are all just examples of different kinds of operators, even the assignment operator. There are different operators, and Then there are rules in programming languages that tells you what is the order of preference of these operators. And basically, what it will tell you is that square brackets are one of the operators that's highest up in the chain. In other words, when this entire statement here is encountered, then the compiler basically checks, because of the square brackets, I must first look at this part. All right. And because the next thing in the list in this order is the dot operator. So then it checks, okay, I must now look at what is to the left and to the right of this dot. But now you will agree with me that if you only consider that now, what does one.id mean? This is what the compiler will try to do. But one.id doesn't make sense. Students1.id makes sense, but to tell the compiler we want to use students1 as a whole, we then basically put the round brackets around the entire students2, which then basically tells the dot operator, consider the entire students2, which basically is now the name of that particular record. All right, the students2 record dot name. In other words, to access that field. Okay, so just don't ever forget to put the brackets around the array when we have such a case. We don't have to put brackets around in a normal situation like we had before if we just have a record structure called student. All right, remember student dot ID, for example, is completely valid. We don't have to put the brackets around student because there's not this problem of the square brackets that might now be confused as well. This will, however, work if we just put square brackets around student, but I mean this works for that matter if you put round brackets around anything. So technically what I've written here will also still work, but student in this case is just the name of the record. It is not an array. In the examples here, we have an array of records, and for this case, we have to put the round brackets around the first array name, so to speak, which is students1, and students1 hosts that particular record, which basically has 3 fields: ID, name, or grade, and we access it specifically now by saying students1.id. So that will assign 1001 in that ID, and students1.name will assign j.aaron, and students1.grade will assign the character A. And that will then have entered, basically what you see here would have entered all the fields of the first record, which basically, and this first record is stored in this first array entry, students1. Similar to read in data for the second record entry, in other words, for the fields that's stored in the second array entry is basically done then by students2.id, which is assigned to 007. Student2.name is assigned f.bush, and student2.grade is assigned the character F. However, we normally use a loop to read data into an array of records. Remember, we said before, loops and arrays, they go hand in hand. And in this particular algorithm, 11.2 here, it shows just part of pseudocode to read student records. So you would typically go and assign your loop counter or your loop variable to 1 because we want to start at student 1. All right, and then this while loop, while I is less than 31, I mean, we assume there are 30 students here. So while it's less than 31, an alternative would be to say here, while I is less than or equal to 30. So that would have worked exactly the same. And so this just shows you there are alternative ways to do things, as long as it logically works correctly. Okay, and then so what happens here, we're going to read the first field from student record number I. So if I was 1 in this case, like in the beginning here, then it would read student I.id. The next one, it would read student1.name. The next one, student1.grade. Then we increment I, in other words, make it one more. So now I would have the value 2. So now when we get here, it would basically say read students2.id, read students2.name, read students2.grade, and so on, until we've read everything. Now this was just an example for reading. You could have just as well assigned some stuff, writing stuff into it, do some processing on it. For example, you could have said something like, not necessarily in this loop, but it's perfectly valid to have a statement, for example, like students students 1 dot name is equal to, and I'm just continuing at the bottom here, students 2, don't forget the round brackets, dot name. So in other words, this would have assigned whatever is the name of students 2 would have been assigned to the same or to the name of students 1. So operations like this is perfectly valid. You can basically, in this case, you read from student2.name and you write it into students1.name. Okay, assigning it basically. All right, so an array and an array of records represent a list of items. We've seen that with the example so far. We can have an array of records. Now, an array can be thought of as a special case of an array of records, which each element is a record with only a single field. Okay. But unlike arrays, records can potentially be broken up into separate memory locations. Assume the memory state currently looks like we have it here. All right, so what we can see here is that here on the third byte, in other words, byte number 2, there's a value 12 stored. Maybe that's some kind of variable. Then we see a number of items from physical position number 35 going all the way up to physical position number 53. And that's a record, most probably a record structure with 20 values. And then we see again some other value stored there. That might be some counter variable or some other variable, who knows. This is just some arbitrary setup that I made here to try and demonstrate to you now a bit how records do differ from, or could differ from arrays. For example, we might have 3 different records, and let's assume just this 1, 2, and 3rd record. All right. So when these 3 records are read in, then basically when starting off with the first one, then basically in this case the entire record for students 1 needs to be stored next to each other contiguously. Alright, so if you just quickly look at this data, the ID is an integer field, or it could be a string field, depends on how you want to implement it. The name field is a string and the grade field is a character. Okay. Now, there's about 6-7 characters there. There's another character there. And let's assume this is also a string. Then that will also take up 4 characters. So basically, the field length, especially when it is about strings, but also other types of variables, they all have a specific length. So in other words, let's assume, as I say, ID was a string, name was a string, and grade was a string. Then technically we must have used the double quotes if this was a string, and so on for the rest. But all I want to show you here is the ID field is probably fixed in terms of it will stay 4 characters long. All right, so that could be a 4 characters long field. The name here, let's assume, in other words, I just want to make a note, so that's 4 characters. Let's assume the name field can be maximum 10 characters, and we know a character type is always only 1 character. So basically, it needs 4 plus 10 plus 1, which basically is 15 characters of storage space for each student record. So those 15, we will not be able to fit 15 characters in there and there, because there is now another variable we assume is stored over here, and only from here the operating system will determine, okay, let's reserve, in other words, the operating system will do that automatically. It will check that this field requires 4, that 10, and that 1, so it knows it must reserve 15. So basically 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 15 is basically what it will reserve for this record, and then it will start storing it. First, as you can see, the ID 1001, which is a character, then the name j dot space, remember space is also just a character, Aaron, and that's 1, 2, 3, 4, 5, 6, 7 characters, and we know the field is 10 in length, so in other words it's just going to leave the next 3 empty, but because it is reserved for 10 characters, and then the next thing is going to be the character, which is A. So there we could see that we've just inserted or stored in memory the first record. Then that basically means we would have been up to here now. So basically all of that is now used. So now the next record needs to be stored. Again, the operating system knows the record length is going to be 15, because remember the record length must always be the same. All of the records will have the same length. So the next one will also require 15, which is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. There's enough space, in other words, so it will basically go up to there. And there is what you can see, the next data. The ID, student 2 ID is 2007, and then the name is f dot space Bush, and 1, 2, 3 characters just left open, and then the grade is F. Then there's now 2 open, but will not be able to host the next record. So the operating system will have to go and check further. Is there now 15 open after this one? 1, 2, 3, 4, 5, 6, 7, 8. No, there's not. So it will have to yet continue over here, and then it will check from here on. It will be able to store the next record, which is basically student 30.id, which is 3012. Then the name m dot space Blair, and 2 characters left empty to make a 10, and the grade is B. Alright, so this is just to show you a little bit in memory how these things would have been stored. Usually arrays are stored all contiguously, but with cases like arrays of records, like in this case here now, it might be split up. But again, this might differ from programming language to programming language, or even operating system to operating system. It just depends on how the operating system is set up to handle memory management. Right, so that's arrays. Let's move over to linked lists, the third and last data structure type that we're going to look at. And as I said at the beginning of this chapter in the previous lecture, most of these, or these are probably arrays, records, and linked lists are probably the three of the most common data structures that you will ever use in programming languages. There are others as well, like tree structures and so on, but we're not going to do them in this course, only these three. So linked list. What is a linked list? It's a collection of data in which each element contains the location of the next element. That is, each element contains two parts, a data part and a link part. So often this link part we often refer to as a pointer or a pointer variable. In other words, it points to the next item in this linked list. In the figure just now, we will look at it and it will make more sense to you. So the name or the identifier of the linked list is the same as the name for this pointer variable. Okay, so we will see in figure 11.9 just now. It shows a linked list called scores. So scores is the name of the linked list, and it will contain 4 elements, as you will see just now. And we define an empty linked list to be only a null pointer. So there is this concept of a null pointer, which basically means it's supposed to be something pointing somewhere, but if it contains the value null, N-U-L-L, all right, then it basically means that that thing is not pointing to anything, and that means it's an empty linked list. So let's look at figure 11.9. So here is a graphical representation of the linked list. So basically it looks like this. It is some kind of structure which basically has a name. So scores is the name of this linked list, and that basically is just a pointer, that thing we call a pointer, that points to the next item in the list. And each of those items, this entire item here in the list, basically is also referred to as a node. So that node usually contains two things. It contains a data part, so whatever is stored in here. This could be a single character, it could be an array, it could actually be a record structure. Usually it's not an array, but we basically store data in there, and then the next thing is the link, which basically is the pointer, yet again pointing to the next item. Then we have the node again, and then we have the pointer to the next node, the pointer to the next node, and so we continue. And the last one you will see over here does not have something pointing, which basically is indicated by this cross. It means that its link is empty or contains the null pointer. Just again, what do we mean with null? Null is a special character. It's one of the ASCII characters in the ASCII character table. So that if it contains the null character, then it basically means it's empty. It does not point to anything. Let's look at it in a bit more detail. So here, before we discuss, we just need to confirm some of the notation we're going to use in the figures. So we show the connection between two nodes using a line. In other words, that line over here with an arrowhead that basically is the connection or the link indicating that two nodes are linked together. As we said, one end has an arrowhead to show to which link it is which new node it is pointing to, and the other end has got a solid circle. In other words, what you see over here, that solid circle is just showing this is where the arrow points from, and generally this line and arrow is collectively called the pointer. That entire thing over there, that is the pointer to the next node. Now we also refer to the pointer as the address, or sometimes a copy of the address that it is pointing to. So note the address. In other words, what we're saying about this particular pointer there, what's actually stored inside this red block here, which we call the pointer, is nothing else than an address. That is technically how it is pointing to a next variable. What address are we talking about here? This is the physical address. So wherever in memory the next node is stored, that address is basically going to be stored in here. Just note that also it is possible to have two separate pointers all pointing to exactly the same node. All right. And what does this mean? It's just that this is a copy of that there. And in other words, the address that's in the first pointer here is just the exact same address that's in the second pointer there. So it is possible that we can get situations, you'll see later, where this can happen, to have a pointer or two pointers, or even more than two pointers, all pointing to the same address. You'll see the use of that later. Right, so arrays versus linked lists. So both an array and a linked list are representations of a list of items in memory. So the whole purpose of an array is to group together a list of items. The same with a linked list. But look how they are differently implemented. We know that an array, for example, here, if the array was called scores, then we have, for example, scores 1 containing the element value 66. Scores 2 might have another value 72, and so on. Okay. We can do the same thing with a linked list. It just looks a little bit more complex. But also look at the order in which things appeared here for the array. It was 66, 72, 74, 85, and 96. It had to be in that order. Now, if we start with a linked list, we must have what we call a head pointer. So in other words, that is actually the name of my linked list. It's like a variable that's called scores, and this variable contains the address, the starting address of the first node. In other words, as you can see there, it literally points to the starting address of the first node of this linked list. Okay, so don't confuse this and think this is the first node. This is actually the pointer to the first node, or the so-called head pointer. It's almost like a node without data. It only has the pointer of the starting position, the starting address of the very first node in my linked list, which then has a data part and stores 66 in that data part. And that now has its link or pointer or address to the next item in the list, which is 72. Okay, so you can see we've done 66 and 72 coincidentally in the same order here. All right, but now if you see, just read from top to bottom, here we see 66, 72, 96. That's actually the last one here. But in actual fact, it is implemented in the way, in the same order, by actually now, if we look at at the second node's pointer, that points to somewhere else further off in memory, to the address of 74, which is actually the third item, like meaning the scores arrow. So that's the third item. But can you see now? It is physically stored in a different place in memory. It's not necessarily next to the previous one. It in turn has its data part of 74, and its next pointer is pointing to the next item, which is 85, like the fourth item in scores as well. So, and it is pointing again to the next item, which is 96, which is like there, the last item, and you can see it does not have any pointer. It has only the null pointer. In other words, the null character. There's no pointer, indicating that is the end of the list. Alright, so now you can already start seeing some differences between arrays and linked lists. Arrays, everything has to be contiguous and in order. With linked lists, it can be stored in several different positions, but the pointer is pointing to the next logical item in the list, but they don't have to be stored next to each other like it was here in the array. So let's try and show you how this really works in physical memory. So again, here we have basically the memory starting at physical position number 0, and then goes 1, 2, 3 up to 9, and then the next one would actually be 10. Sorry, I see there's an error in there. This should have actually been starting at 10 and then 20 and so forth. Anyway, for now it's not too important. What you just need to realize is that what I've got here in green is an array. So you can see this array here, over here, actually has got 1, 2, 3, 4, 5 elements. And what is this? This strange looking element here. That is actually how an array is really implemented in memory. That's actually just the name of the array, which, and in actual fact, is also just a pointer to what? What does it say here? 0063, in other words, physical address 63. Where is physical address 63? 63. So in other words, the intersection is there. In other words, an array, in a way, also actually has a pointer where the name of the array is pointing to the first item in the array, which is always just next to it. We didn't specifically say this before about arrays, but now you know. This is really how the array is implemented. Its name is actually just also the address of the first element, which is literally just next to it. Okay. So element number 1, or the first element over here, has the value 66. The next one 72, the next one 74, 85, 96. Alright, so those 5 elements. But now I'm going to show you how something like that can be implemented by a linked list. So the orange/pink, I'm not too sure what this color is called here, but let's assume it is an orange or pink color, doesn't matter. So where will be our head pointer? Okay, so we know the first item is supposed to be 66. So if you just search in memory here, then actually you'll find item 66 over there. But the pointer always starts, or the very first pointer is always the head pointer. So as an actual fact, this particular item here is the head pointer of my linked list. And what does the head pointer do? It points to the address of the first node. In other words, it contains the address of the first node. The address of the first node is 75, as you can see there, which means 75, and the intersection is basically here 66. In other words, it points to physical position 75 in memory, which means that's the first node. And it has its value of 66. And the next part of it, the link part of it, as you can see over there, now points to the next item in the linked list. That's the address that it points to. In other words, physical position number 6. In other words, so sorry, let me just show my animation that I wanted to show before. So there's the orange one is the head pointer, 6, which means 6 is now pointing. It's pointing to address 6 here, which now contains 72, as you can see there, and it is now pointing, its link is pointing to address 8, which coincidentally is just next to it, but that's also a possibility. It can be next to each other, not always. And then again, there is 74 with its address 103 pointing to address position 103 over here. And it, in turn, its data value is 85 with its address 0043. In other words, it's pointing to address 43, which is basically this one over here, containing the value 96. And sorry about this. Ignore that strange scribble there. But basically 96 is this one over here, and it has the null pointer, as you can see over there. So the null pointer basically means it's the end of the list. It's not pointing to anywhere else, which basically means we are done. Right. Okay, so linked lists, names versus node names. So as for arrays and records, we needed to distinguish between the name of the linked list and the names of the nodes. All right, how did we do this with an array? This we're going to draw on the screen here. So for an array, we had, for example, student, and we referred to a certain element by saying student 2. That meant it was the second element in this particular example in an array. Or a specific field, if it was a record, we could say, for example, students student.id to refer to a specific ID field in the record. How then do we refer to a specific node in a linked list? And a linked list, we know, first of all, must have a name, scores, and that's basically the name of the variable of the head pointer. So it's basically the name of that variable is called scores, which we know is the address of the first element, pointing, in other words, to the first node over there. And nodes, on the other hand, do not actually have explicit names, like in a array where we, if we did look at student 2, we knew exactly which element we were talking about. Or if we talked about student.id, we knew exactly which field we were talking about in a record structure. But we don't have something similar in linked lists. We can't say scores 1 or scores 8 or whatever to refer to a specific element. How then are we going to do this? And we're going to have another trick, basically, where we're going to have what we call a current pointer. Now, the current pointer initially has the same address as my head pointer. So if the current pointer has the same address or a copy of the head pointer, it just means that the current pointer is currently pointing at the first item in the node. How then do we advance this current pointer to the next node? Well, let's say, for example, it was initially pointing to this first node. Then let's say, for example, just for argument's sake, what I'm going to do now is I'm just going to maybe write down arbitrary addresses. Let's say this node was starting at address number 45 in physical memory. Maybe this was at address 49. Maybe this was at address 13 for that matter. Maybe this was at address 22. So you can see in all different places in memory. So initially, if the current pointer was pointing to the first item, then basically both scores would have the value 45 and current pointer would have the value 45 inside of it. Just means they're pointing to the same thing, which is basically the address of the first node. Now, if we advance the current pointer, so let's say, for example, the current pointer was now also, as I said, pointing to the same thing, so it's just a variable which has the address to the points. So if we want to advance the current pointer to the next item or the next node, then we want it to point there, correct? So all we need to do is to change this address of 45 then to 49. Then it means the current pointer is in actual fact currently pointing to that address. It doesn't mean like scores that never change, right? The scores is the head pointer always stays the same, always points only to the first element. But as we say, if we want to keep track of where we currently are in this linked list, we must have an additional pointer, which we call the current pointer. It's just a pointer variable. It's a variable that can store an address. And so again, if we want to advance it yet again to the next node, to point to the next node, we know we have to change its address then to 13. But now, we don't necessarily have to keep track of the actual physical address values. Luckily, in programming, the operating system keeps track of that. All right, so there are common methods and ways to traverse through a linked list. In other words, to go from one node to the next without having to know the actual physical address. And we will see how to do that in the next lecture though, so I don't want to run that ahead. All I just needed to point out to you now is this special additional variable, which is the current pointer, which we use to basically identify to which element we're currently pointing at. In this diagram here, technically, where this pointer is now pointing to this item, technically it should really point to where the address starts, right at the beginning, because that's technically what it does. All right, it's not pointing to somewhere in the middle here, because remember, this might be a record in itself, or it could be a big variable, so it might actually consume a number of bytes here. You know, so it's technically just pointing to the very first byte of this particular node. And yeah, some syntax to look at. So again, when we talk about the data part or the data item of a certain node, when we talk about this particular data item, we're going to use the .data operator. In other words, this will refer to the data part, and again we have to put scores in brackets and a little star before scores. In programming languages like C, C++, Java, and so forth, when we put a little asterisk before something, it actually means pointer. In other words, basically means that whatever scores points to, what a score points to, it points, it's the head pointer, it points to the first item in scores. But what specifically, remember, scores, the node, or that node consists out of two parts, a data part and a link part. So if we just want to refer to the data part or get access to the data part to read whatever is in there or to write something in there, we use scores.data to access only the data part. To access the link part, in other words, to change the link, to make it point somewhere to the next item, we basically use the same. We say scores. In other words, what does scores point to? Scores points to the first item here, the first node. And what of that first node? Dot link. In other words, then we refer to that part, the pointer to the next item again. All right, and then as we've said, this is one way. Well, this is one way to refer to the data part in exactly the syntax that is listed over here by saying asterisk scores in brackets, don't forget the brackets, dot data. All right, just take note there's no space there. It might look like there's a space, but it's all together. There's no spaces in here. But there's an alternative way. It's the same as saying scores arrow data. And this arrow is just simulated with a minus symbol and a right pointy bracket, that we call it like that. So it can't be the other way around. It can't be like this. It has to be minus and then the pointy bracket. So this means exactly the same as that. So it's two alternatives. Whenever it's required from you to use any of those, you can choose which one you use unless we tell you which format to use. And then we will call this over here the arrow format, and this we will call the dot format. Okay. But this is where I want to stop for now. So in the next lecture, we will look at what can we do with a linked list? How can we traverse through it, and what's the actual nice uses of a linked list that makes it actually quite powerful. Thank you very much and enjoy the rest of your day.